What's up, dudes? We get to this place here where we are able to talk about another instance of an object moving in a circular path. Now, orbits we have to talk a little bit about, but let's assume that object with mass m here moves in a circular orbit around let's call it a planet of mass big M. And what we want to be able to talk about is how fast does that thing have to move to maintain an orbit of radius r. And notice where r starts. R starts, at the center of that, the center of the orbit. Of course it does. All right. Now, well, you can see that. Well, what we could say for this object is there is a force that pulls inward. Of course there is. And I'm going to write it as a gravitational force. All right. And so we can say that Fg is MAC, or Fg is mv squared over r. Well, Fg is mg, the weight of the object. Now you notice I haven't used this big M. All right? This force is the force that acts on that object, the object that moves in a circle. This mass is the mass of the object that moves in a circle. So we're talking about mass little m. And what we end up with is this expression that we've actually seen before. We've seen that somewhere else. But this is different than the other one. We've actually seen that one in this case. Something moves around in a loop like this. And at the top, what's that magic speed where it doesn't come in contact? It just loses contact with that track, let's say this is. Well, that's an mg toward the middle, right? Well, same thing, is mv squared over r. The difference here is that this g is g near the surface of the Earth. I mean, g, by definition, is gravitational acceleration. We know what that is near the surface of the Earth. We know it's 9.8 or 10, whatever you want to call it, meters per second per second. But not near the surface of the Earth, quote unquote, g is not constant. I mean, g isn't really constant anywhere. It's pretty darn constant, but it's definitely not at some, big altitude above, say, Earth. It's not 9.8. All right, so we actually can't find this speed just yet. And we can't answer this question either, because it depends on this gravitational acceleration, or really gravitational field strength. Same thing. Okay, so I transition you now to the next set of notes, your gravitation notes. If you don't have them handy yet, grab them. All right, ooh, outer spacey. So eventually, what we want to get to is this question. All right, we know the short answer, dig, this is cool. Do you know the short answer is that it's got to go that fast? All right, but we need to figure out, eventually, how is it that we express gravitational acceleration or gravitational field strength as a function of some other stuff? All right, it's one of our intermediate steps. We'll come back to this question. This is sort of our culminating question for the circular and gravitation units kind of treated as one unit, okay? If we put the circular stuff aside for a minute. Oh, looky, a circle. If we put the the circular stuff aside for a minute, we talk about the idea of gravitation, all right? And again, let me remind you that we're sort of looking at some other, quote, other forces right now. All right, we've talked about WANTF, just sort of in general, and then we said, well, sort of what can some forces do? They can make things twist or try to twist. We refer to that as torque, right? We talked about when forces can make things move in circles, so some special applications of forces. We've talked about the fact that there is such thing as gravitational force. We've written it as mg. We're going to get more specific with that. So again, another maybe more detailed look into a certain force here. We call this universal gravitation. So the question right off the bat is, what objects are attracted by a gravitational force? Well, the answer is all of them. Every two objects in the universe are attracted to each other. You right now are exerting a force on every single object in the universe, no matter where it is, no matter how big it is or how small it is. And every single object in the universe right now is pulling on you. I am currently pulling on you. That's why we call this universal gravitation. Newton has a pretty busy year after he gets out of college. He goes back to his mom's house. That's what I did. I went back to mom's house too. But I painted fences and pulled weeds for a few months. And he developed his 3 laws of motion and universal gravitation and developed a little something called calculus in a year. So it's a little bit more productive than me. But yeah, universal means everything attracts everything else. All right? Let's look at 3 pairs of masses. And let's assume that the actual size of a mass is related to its mass. That's not true, but let's just assume it is for now. And the question is, which pair feels the greatest gravitational attraction? Take a guess. Pause if you must. All right, so yeah, it's pair 2. No, it's not, you jerks. It's not pair 2. It's pair 1. No, of course, it actually is pair 3. Pair 3, each one of those feels the largest force. All right, and what that says to us is that, first of all, you can't have a gravitational force without 2 objects. All right, and what it says is the more total mass those objects have, the greater the gravitational force is. Or really, if we call these M1 and M2, to distinguish between the 2 of them, we say that what has to happen is the gravitational force, remember this, is proportional to the product, multiply, the product of the 2 masses. The greater their product, the greater the total force. Well, the greater the force that either one of them feels. Okay? No, yes, right. Yeah? Okay. Now, let's look at these 3 sets of masses. What I've done is, well, notice back here, we actually kept something constant. Well, it might not look like it. We kept the separation between masses constant. Because when we talk about the separation between masses, we talk about the distance from center of mass to center of mass. All right, so all these have the same separation. All these have the same mass, but different separation. So the question is, which pair or which object feels the greatest gravitational force? Well, clearly it's not the one in the middle, right? The closer things are, the greater the gravitational force they experience. So smaller separation, bigger gravitational force. That suggests, and what we call an inverse relationship between gravitational force and separation. We call it R. R is not radius here. It's separation between objects' centers of mass. But it ain't just an inverse. It's actually an inverse square. So combining our findings, right? From the last page, we had that Fg is proportional to the product of the masses. So we put all these together, and we get M1, M2, there's a times in there, over R squared. Except for this thing. But what this says is, if we took 2 1-kilogram masses and put them a meter apart, they do not pull on each other with a force of 1 Newton, right? It doesn't work out that 1 times 1 over 1 squared gives us 1 Newton of force. Think of 2-kilogram masses placed a meter apart. They don't pull on each other very hard. And that means that there's another something in here. And the other thing is this, that you know what a Newton is. You know what the unit of force is. It's a Newton. And a Newton is not a kilogram squared per meter squared. That's not what a Newton is. So this universal gravitational constant G makes the numbers work out right. It takes that, that force and makes it a lot smaller. And it also makes the units work out right. If we isolate G, we get that G is FR squared over M squared. So its units are Newton meters squared per kilogram squared. That's how it makes the units work out right. Okay? So 1 kilogram mass and another 1 kilogram mass separated by 1 meter feel a force. They exert a force on each other of 6.67 times 10 to the negative 11th newtons. And you don't divide that force by 2 or anything. Each one of them experiences that force. Right? Yeah, big G. Where does it come from? Well, Newton, it came theoretically from Newton's work. All right? And I'm pretty sure from looking at a bunch of data that people like Johannes Kepler and Tycho Brahe had collected painstakingly over years and years. I mean, a couple centuries, I think. I might be stretching that, but with a lot of data to look at and a bunch of theoretical development of his equations, G comes out theoretically. But a guy named Robert Cavendish built this thing to find an experimental value of G. He hangs this thing called a torsion wire, which you can imagine just like a metal strap. Like imagine imagine like a long belt, right? It's basically like just kind of like a 2-dimensional strap. Sure, it's got a little third dimension, but it's real thin. All right, and it can twist. It takes a certain amount of force to twist it some, angle theta. All right, and then on the end of the torsion wire, he puts this thing like a barbell with the mass on each end, and then he puts these 2 big stationary masses on the ground, and the force of gravity pulls this mass from here to there and pulls this one from here to there. And he's able to measure how far apart they end up and what angle they've swung through. And he knows some constant, we'll call K, about that torsion wire. So he knows how much force must have been exerted in order to make it rotate that far. And he knows the mass of these things. So he actually backs out and calculates G experimentally. And he gets like within a factor of 2 or something like that, which is incredible. You build this somewhere in your basement, and you get G within a factor of 10, I will guarantee you an A for the 4th quarter. We'll discuss the particulars. No one's ever done it because it's really hard to do. But you think you can do it, and we'll talk about it. Yes, you'll still have to do all the work, but I guarantee you'll get an A and a ringing endorsement / recommendation for me for college. Okay? Next. Here's an example. All right, so we have a couple of masses. We have a separation. What's the force of gravitational attraction between them is a crappy way to ask it, but what's the force of gravitational attraction that each mass feels? So we say F is G M1, M2 over R squared. 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared times 25 times 40 over 2.5 meters. Don't forget to square. Oh, gee, I don't remember what you get. It's like 1.09 times 10 to the negative something. I don't know. You tell me. All right, and then you have this. You have, an object. You got you got the 40 kilogrammer over here. You got the 25 kilogrammer over there. Which one pulls more? Which one experiences the bigger force? So you tell me that tomorrow. All right, which one pulls harder? Now, instead of doing what we call a single well, a two-mass problem like this, we can do what we call multiple mass problems. All right, and so we could look at a case like this. There's a blue mass in between these two other ones, and let's figure out the net force on it. Well, the green mass exerts a force on the blue one like that. I'll call this 1, and I'll call this 2. I call this F1, the force that number 1 exerts on the blue one. It pulls the blue one towards it. F2 is going to look like this. Why bigger? Well, because this distance, R2, is less than this distance, R1. Therefore, the force it applies is bigger. And then we can say the net force exerted on the blue one is just F2 minus F1. Yeah? And how do you find F2 and F1? Well, you need to know what this mass is. You need to know what those separations are. And then you'd plug that stuff all into GMM over R squared and GMM over R squared, and we'd be fine. Now, here's a case where the separations are equal, but now the masses aren't. So, again, I'll say F1 looks like this. This is number 1. And this is number 2. F2 has to be bigger. Since mass 2 is bigger. Again, we would say that the net force is F2 minus F1. Can you write that more simply? Using what we know here and what I've told you about the masses. Come back tomorrow with a simpler expression for that. Now here we say, where do you put the blue one such that the net force on it is 0? Or really, where we're saying, where's the net gravitational field 0? You tell me that tomorrow. Forget about the gravitational field part. Answer this question. And put the blue one somewhere, it would experience 0 force. Generally, I don't need a mathematical answer. We'll be able to solve the mathematical answer soon. But tell me, in general, where the blue one goes.